and I want you to come up with f, g, and h. So I want you to go backwards from this. Yeah, it's a backwards, a reverse. What we're doing is we're decomposing a function into its smaller pieces. I'm going to give you a new example, all right? So I'm going to start with something a little more simple than this. But do you see that if I start with 3 functions and compose them, I can come up with some new function? So if I begin with a function, we may be able to decompose it into smaller functions. So next example, let's let capital M of x be equal to square root of 3x plus 1. Find an f and h, or we'll say g, such that capital M of x equals f of g of x. So what we're saying is we think that capital M can be rewritten as the composition of how many functions? 2. What are they?
So then g could be like 3x plus 1.
I'm going to write down f of x and g of x, and then you're going to tell me what each one of them has to be.
Okay, so g would be 3x plus 1.
3x plus 1, because you see that that's living inside of the square root. And then the
Square root of x.
f is just the square root of x. So if I take, remember what this means. This means g goes into f, right? G goes into f. So if I take this g, I plug that into that f, I would get back that, wouldn't I?
Yeah, but sometimes we're going to come across some that are a lot more complex.
Not really. I mean, it's not, we're going to do maybe some that have 3 or 4 in them, but it's the same principle. It's just a matter of thinking through reverse of what you were just thinking.
What will give you this number? You should break it down somewhere.
Let me ask you something. Is that answer unique? Could somebody else have come up with a different one?
Certainly.
Okay. I'll say or here. Can someone make it happen a different way? How about this? I'll just help a little bit. What about that? There you go. Then this would have to be the square root of x plus 1. Wouldn't it?
And then theoretically, there's infinite possibilities of how to do it.
You could get real crazy with changing things around, but what I'm getting at is that it's not unique. There's not a unique decomposition, but there's ones that make sense and ones that are a little bit nonsensical. This one, I think, is the most natural answer. This one is just not as natural, but it still does the job, right? Still works, exactly. I mean, I could maybe come up with something else. I could do like g of x. I could do like 3x plus 1 squared, and then call this one the 4th root of x.
Which would just be, wouldn't it, I mean, counterproductive.
Yeah, so yes, you could keep going all day, but I mean, that's just like, that's not the point. Remember what I said earlier.
Keep it simple, stupid.
In calculus, here's the goal. In calculus, what we're trying to do you remember this whole idea of
There are many paths to get there.
now, the one where we were trying to find the slope of that line, and we used the difference quotient? Do you remember I showed you there was a shortcut, a super shortcut for it? No, there was, we did the difference quotient, and then I showed you like if you have like x cubed, that you could bring the 3 down and subtract 1. Do y'all remember me showing that? Okay, there was a shortcut for it. Well, in Cal 1, you're going to be asked to find the slope of the line, the tangent line like this, and this is the function you'll have, right? That's a very difficult problem to do. So what we do is we decompose this into 2 smaller pieces. Now, do these look familiar to you?
Yeah.
These are things you should recognize. This is a linear function. This is a square root function. These are part of your toolbox functions, right? That we need to know about. Part of the reason we need to know about their behavior is because later on we take complicated functions and we try and make them easier to look at. So we say, we just look at the pieces, figure out the answers, and then put the answers back together to get us back up there. So, okay, let's do another problem. I'll give you capital S of t. How about that? I'm going to give you a different variable, S of t. And what I'd like is for us to consider, these don't get too complicated here in your book. I don't like that. So how about 1 plus 1 over x squared, like that. Cubed.
Plus negative how?
Plus 2 absolute value.
You know what, just square all that.
What? What? All right, so let's see if we can do this. Find f, g, h, j such that capital S of t, oh wait, change that x to a t. Sorry, I changed the variable. That's a t right there. Equals f of g of h of j of t. So I want us to somehow see that this is a composition of 4 things. So there's several approaches to this. The last one I just asked for the answer and someone gave the answer and that was it. We were good. But on this one, let's be a little more systematic. Let's think about the last function and work our way in. What is the last function you see happening?
Absolute value.
You think you want to work with like an absolute value? So maybe that's what we should let our, which is the last one?
No, I'm sorry,
F. Okay, maybe we should let the F be absolute value of x. I'm okay with that.
So it would be x plus 2, or no, 6.
You could do x plus 2 also. What do you want to do?
Hey guys.
Yeah, sorry, t. T. You could do absolute value of t plus 2.
I think
It's your call.
G could be
Y'all want t or t plus 2?
T plus 2.
Just absolute value t? Okay.
T to the cube plus 2.
Oh, you want the cubed also?
Yeah, just get it all in one.
Yeah, you could do that also. But would you agree that that's the like cleanest one though?
Yeah, that's the claim.
That's the cleanest one, and that's what you want in Cal 1. You want clean, all right? I think that's the cleanest function. What would the next thing down be? So you have plus 2, right?
T plus 2, so T plus 2.
So what are we at? G?
Or we can do that.
You want to go t plus 2? Okay, now what?
T cubed.
H of t, you want to go t cubed? Yeah, we are running out of letters.
That's why I'm saying we need to.
We only have one option for the next one, don't we? H of t, j of t would be 1 over 1 plus 1 over t, wait, sorry, 1 plus 1 over t squared. That's our only option?
That's not very.
That last one's not very pretty. But see, in Cal 1, no one tells us we have to do 4 functions. We could do as many as we need. So in Cal 1, I wouldn't stick with 4. I'd probably go to 5 or 6 here if I wanted to break it down. You know what I'm saying?
So like then could you do like 1 plus 1 over x, and then for the next one, like for the
Yes, and then,
do x squared
yes, t though, yes.
or
Uh-huh.
t, you know. So also, yeah, I don't know if you can say this. So possibility would be 1 plus t cubed, and then you can go into 1 over t squared, which is another one.
That's
1 over 1, yeah, you could say 1 plus t quantity cubed and then your next one would be 1 over t squared. Yeah. So you see how there's not a unique answer to this? There's going to be different variations of this. That's why, when I grade these, I look and I just make sure, all you have to do to check is plug back in, right? If I take this, plug it in right here, right? I get that piece. And if I take that answer and I plug it in right here, I get this piece. If I take that answer and plug it in right there, I get the absolute value, so I'm good. All right. Next problem is a word problem. All right. This is going to come out of the book. I'm going to write it down because I know not everyone has the book with them. The volume 60 on page 409. The volume in cubic meters of a balloon is V equals 4/3 pi r cubed. If, hold on a second. If the radius increases according to R of t equals 2/3 t cubed, then find the volume as a function of t. Now here, let me just add one thing. T is in seconds, and R is in meters. All right. So let's try and interpret what's going on here. This problem is leading you into calculus, all right? This is the type of problem that you see, at least to start, in Cal 1. This is the beginning of the problem. You have a balloon, right, which we're going to assume is spherical. I know all balloons aren't spherical, but we're going to assume that we have a spherical balloon, all right? 3-dimensional, so it's got some depth to it, right? We are given that the volume of this is 4/3 pi r cubed. That is the volume of a sphere, a solid ball. 4/3 pi r cubed, where r is the radius. So if you know the center of the sphere, you're able to measure out to the edge. That's your radius. The volume is 4/3 times pi times the radius cubed. So if someone gives you the radius, you can give me the volume, right? But what's happening is that someone is pumping air into this balloon, and this balloon is growing. All right? It's growing in such a way that as time passes by, in seconds, the radius is changing as a function of this time. So the radius is changing as time goes by because the air is going in, it's getting bigger, right? So at t equals 0, what's the radius? At t equals 0, right? You get 0 radius, so we have no balloon, right? At t equals 1, what's the radius? 2/3, and then I could find the volume, couldn't I? I could take that 2/3 and plug it in here and then find the volume. At t is equal to 2, I get what? 16 over 3, 16 thirds, something like that. Then I could go and find the volume. So every time someone gives me a time, I should be able to go and find the volume, shouldn't I? What we want to do, instead of having to like get the time and then plug that in for, get the time to get radius and then radius to go get volume, we just want a function that gives you the volume when someone gives you time. All right? This is composition.
Oh, I see.
Do you see its composition?
Yeah.
We want to take, these are basically two functions. Right now, this volume, you could almost write the volume is actually a function of the radius, right? The volume, to know the volume, you must be given the radius. This says to know the radius, you need to know time. What you want at the end of the day is your volume as a function of time. You want v of t, which means you no longer want r in here, do you? What can you replace r with, though? 2/3 t cubed. So it's just taking that and plugging it into this. So really this question is just asking you to find v of r of t. That's all they want. V of r of t. So plug in, what? Let's take 4/3 pi, and then instead of r, we're going to use what? 2/3 t cubed, but then cube again, because that's r cubed. Now let's go ahead and cube this. What happens when you cube 2/3? Cube top and bottom. 2 cubed, 8. 3 cubed, 27. What's t cubed cubed? It's either 6 or 9, right? 6? 9? It's a power to a power. You multiply. So t to the 9th. And let's see if we can get that a little cleaner. 4 and 8, 32. 3 and 27. 81 pi t to the 9th. That's it.
I have a question off topic.
Yes.
Did you observe Pi Day?
I did remember it. I didn't really do anything special.
Although
Did it make it higher?
sadly was the last year, was like the only year that we will ever get a very accurate.
Yeah, last year was better than this year. It was kind of a
last
bummer.
year Pi Day was like the best Pi Day that we will ever have in our life.
In our lifetimes, yeah. Because the last two digits of the year, y'all know what pi day is?
Yes, 3.14.
Yeah,
Yeah, but last year was 15.
pi is 3.1415. It keeps going. Last year was March 14th, 2015 was the first digits. That won't happen again. That's the best pi day ever.
Not for another 1,000 years.
Yeah, in our lifetimes is what he said. Although we talked about there is a probability that we will all live another 1,000 years, right?
And this was full of Walt Disney cruises.
Sir,
Yes.
yeah, we're just gonna freeze ourselves and have our bodies unthawed just before the day.
Sounds good. Sounds good.
My life is nothing but celebrating Pi Day and then freezing myself in.
All right, I don't think there's anything else on this section for us to, there's one more little thing, sorry. I'll show you something real quick. The homework for this section, go back to the calendar, the schedule for the semester. Go back to that now and do the homework there. You should be able to handle everything, except this one I didn't really talk about. I'm not going to copy this one out of the book. I just want you to see this. I'm going to draw a picture real quick. Let's say we have 1, 2, 3, 4. 1, 2, 3, 4. And I'm going to have to draw, let's see. That's G. I just graphed two functions, all right? I want us to find f of g of 0. Okay, so think about the path that we were discussing earlier. If that was f of g of x, x goes where first? If that was f of g of x, where would the x go first? Into g. So that means I'm going to take 0 and I'm going to plug it into g, right? So what does g spit out? At 4, right? At 0, it's 4. And I'm going to take that number and I'm going to plug it into f. And what does f do with 4? Here's 4 into f, 3. See that? That's it. The answer is 3. Now let me see if I can do another one. How about what's g of f of 2?
0.
Yeah.
0? So what happened there? 2 went into f first, right? So 2 into f, here's f. 2 goes into f, it spits out 2. That answer, 2, goes into g. When you plug 2 into g, you get 0. There's a problem number 11 in the book where they give you a picture and then they ask you to find some different things. That's all it is. Since I do have, I promise I won't keep you more than another 3 minutes, but let me just get you to think about something. What if I had a function that did this? What if I had a function f that it took, let's say, 2 over to 6. It took 3 over to 9. It took 4 over to -1. It took 0 over to 5. Okay? Let's just say that's what happens with f. All right? Then I have another function, g, which takes 6 over to 2, 9 over to 3, -1 over to 4, and 5 over to 0.
It would be an inverse of whatever the f.
They're undoing each other, right? They're undoing each other. Whatever f does to 2, if I take that answer and send it back through g, it's going to take it back to 2. Now I want to show you with a picture what this would look like. So let me do the f in red here. If I go to 2, I'm up here at 6, right? If I go to 3, I'm up here at 9. Y'all okay with that? If I'm at 4, I'm down here at -1. And if I'm at 5, if I'm at 0, I'm up here at 5. Yeah? Now let me show you the G one in blue. 6, I'm at 2. 9, I'm at 3. -1, I'm at 4, right? -1, I'm at 4, right about there. And then 5, I'm at 0. Got it? There's something going on here that is hard to see in this picture, but imagine if you draw a diagonal like this. Okay, do y'all see that? Now that's the good old function y equals x, isn't it?
Yes.
If you look at these and kind of tilt your head this way, it's not a very good picture. But let me just like connect these 3 dots together.
But we get the idea.
Right? And if I connect these 3 dots together, you can kind of see that these are looking like mirror images of each other. Whenever you have a function that undoes another function. I said they're going to be called inverses, right? That's next class. Geometrically, they will have to be mirror images of each other over this diagonal line. So when you go back and you look at, think of these two functions, x squared and square root of x. Those should undo each other, right?
Yes.
Like if I take that and plug it in there, I should get x. If I take that and plug it in there and I square, I should also get x. And if I were to graph those two, that's x squared. What does square root of x look like? We know it's this piece right here, right? Just that right side. We have a little bit of a domain issue that we'll deal with next class. If I cut the left side of this off and then I draw my diagonal, you can see that those are mirror images of each other. So that's what next class is about. These are called one-to-one functions. Do your homework. I'll see you on Thursday.
The tester,
No, everybody,
Yeah.
all of my friends.
Anybody who needs to get their test still,
Oh, yeah.
I have them up here.
Really? I've seen a couple.
There you go, sir. I think the grade's on the bottom of the second page.